Okay, so now that we know what vector valued functions are and what they represent, curves in space, we can now talk about differentiation and integration. This is, after all, a calculus course, right? So this had to come up sometime. So now we can talk about the derivative of a vector valued function. And it's defined, well, the way the derivative was defined back in Calc 1, right? The difference being that these are vectors and not, functions of what, they're functions of one variable, but they have three separate, 2 or 3 separate values, right? Their values are vectors, components of a vector, right? So yeah, but we take this as the definition of the derivative, right? And we know what a derivative is for a function of one variable, or I should say for a single valued function, but it's the same for a vector valued function, right? So, and we should also say that, let's suppose r prime, right? So so we should say that this is r prime of t. I forgot to mention that. Okay, so this is equal to r prime of t. Right, so if r prime of t 0 exists, right, then we just say that r is differentiable at t0. Differentiable, right, at that particular value of t. And of course, it's differentiable on an interval, if, right, so r is differentiable on an interval I. Could be an open interval, closed interval. Typically, we'll use the closed interval, say from A to B. Right, if it is differentiable, right, for all t on the interval I. Okay. So, yeah, and you might remember from way back in Calc 1, at the very beginning, when we took derivatives, we had to use the definition. And so if you're thinking, you mean I have to use the definition again? I got to take all these limits and calculate the difference quotient? Luckily, no, right? So there's a property, theorem 12.1, which guarantees that you can take the derivatives in the usual way, and you end up with essentially the same thing, right? So here's what the theorem says. If I have a vector valued function, right, given with the 3 components, right? So let's say x of t, y of t, z of t. Those are the 3 components. Then the derivative, right, so r prime of t, or if you prefer, you can write dr over dt, right, same thing. Right. So that's just going to be the vector valued function whose components are the derivatives of each component function separately. So you can think of it as x prime of t is the first component, y prime of t is the second component, and z prime of t is the third component. If you'd rather write them as, dx over dt, that's fine. But these are just ordinary functions. Sorry, that's a t. So how do you calculate the derivative of x, or the derivative of y, or the derivative of z? The same way you did that in Calc 1 and Calc 2. Okay, so yeah, so this should not come as a surprise. And in fact, let's just do a very quick example here. Suppose r of t is given by, I don't know, t to the 5th power minus 3 times t. And then let's say y is the natural log of t. And then let's say that z is, I don't know, tangent of 2t. Something exotic like that. All right, so that's our vector valued function. Right, and you have to worry about the domain, of course. Obviously, t has to be positive, but it cannot equal an odd multiple of pi over 2 plus n pi, right? Yeah, so pi over 2 plus n pi. So effectively, we're confined between 0 and pi over 2, I think. That's sort of the biggest interval we can use here. So that's the domain. But we want the derivative, right? So how do we take the derivative? Well, we just take the derivative of each component function. So you better know how to do this by now. 2 times secant squared of 2t, right? Okay, so if you didn't know how I got these functions, well, look back in your Calc 1 and Calc 2 book. On the front cover, they'll have a list of formulas for the derivatives, and you should refresh your memory because we're going to be doing this a lot, right? So make sure you're kind of used to, basic derivatives. I'm not going to look for anything fancy like the, hyperbolic cotangent of, the cube root of e to the t or something crazy like that. But the basic functions, right, the trig functions, exponentials and logs, yeah, we're going to see those a lot, right? Okay, so that's finding the derivative. Okay, so here's another one, right? U is equal to t cubed times I plus square root of t times j minus e to the 3t times k. So it's another vector valued function in space. And they're asking for the first derivative and the second derivative. So you know how to take the first derivative. We just did an example of that. Right. Again, you can also write du over dt. And let's stick with the same notation here, right? So this will be 3t squared times I, and then plus 1 over 2 square root of t times j, and then minus 3 e to the 3t times k. I don't think I need parentheses anywhere here, although, you always have the option of putting parentheses around it if you want. So that's the first derivative. So how do you find the second derivative? Just take the derivative again, right? It's d squared u over dt squared. So this will be 6 times t times I. And then this, oh boy, so this will be minus 1 over 4 times t times the square root of t, right? So t to the negative 1/2, so 1/2 times negative, I think that's right. So that's times j. And then minus 9 times e to the 3t times k. Okay, so there's the second derivative. And obviously you can take the third derivative, fourth derivative, but typically we'll just do 1 or 2 derivatives. Right, and remember, these are vectors, so we can add them, we can subtract them, or how about this? Here's a good example. Let's find the dot product of u prime with u double prime. Right, so we're taking the dot product of the first vector here with the second vector. So you remember the dot product, right? You just multiply the corresponding components. 3t squared times 6t is going to be 18t to the 3, right? Plus, right, well, this times this. And so let's see, it's a negative, right? So minus 1 over 8, right? 2 times 4 is 8. And let's see, square root of t times square root of t is t. T times t is t squared. So negative 1 over 8t squared, right? And then, let's see, plus 3 times 9 is 27. And then e to the 3t times e to the 3t is e to the 6t. So good enough. You could try to simplify it if you want, but I think this is fine. Right? Remember, it's a dot product. It's a scalar product. There's no I, j, and k here. A lot of people like to do that, and you're going to get it wrong if you do that, right? Because this is not a vector. It's a dot product. If you write it as a vector, it's wrong, right? Right? So yeah, so please don't put ij's and k's in here. This is a scalar function, right? So think of it as like an f of t, right? So it's a real valued function of t. You know, if you plug in t equals 1, you get a number, right? You get 18 minus 1 over 8 plus 27 e to the 6. Whatever number that is, that's a number. It's a scalar, right? A different t will give you a different scalar, to be sure. So when I said it's a scalar, I mean it's a scalar function, right? It's an ordinary function, like a calc 1 or calc 2 type of function. Okay, right? And conversely, if something's a vector and you write it as a number, right? Like if you write, you know, u as a vector is equal to 7, well, this is also just as bad. This is horrendous because 7 is a number, a scalar, not a vector. So, you know, if you meant 7 times I, then make sure you put the I there, right? So yeah, vectors are not scalars. Scalars are not vectors. Okay. So we come to the definition, another definition here. We say a parameterization of a curve C given parametrically, right, by this vector valued function R with the 3 component functions, right? So this parameterization is called smooth on an interval I if 2 things have to happen. The derivative of R is continuous, right? So you can say, well, does that mean that the derivative exists, right? Is the derivative is a differentiable, in other words? So this is a little bit stronger, right? You can have a derivative that's not continuous, and that would not be smooth then. So yeah, the derivative has to be continuous. So this is a little bit stronger than just saying that R is differentiable. So certainly R has to be differentiable, but on top of that, the derivative also has to be continuous, which is not always the case, right? Okay. And the magnitude or the norm of the derivative cannot be 0, cannot be the 0 vector for any t. Oh, I'm sorry. No, not the magnitude. Shoot. So yeah, see, I made the same mistake, right? I had a number on the left and a vector on the right. So no, I just mean the derivative of R is not 0. You could also say the following, right? This is equivalent to saying that the magnitude of R prime is not 0 as a number, not as a scalar. I mean, as a scalar, right? Not as a vector. So yeah, when I had the vector over the 0, that does not make sense. But now it makes sense, right? So if the magnitude of a vector is 0, then the vector has to be 0. If the vector is the 0 vector, then of course it has magnitude 0. So it works both ways. Okay, so yeah, the derivative cannot be 0, right? Right. So I don't want to get too deep into this, but you have to be very careful here. Right, so if I draw a curve like this, and you say, is it smooth? You might be tempted to say, well, sure, it's smooth. But I'm not talking about the curve. I'm talking about the parameterization of the curve, right? So depending on what R we choose for this curve, and there are many different R's we can choose for this, well, some of them might be smooth, some of them might not be, right? One thing you can say for sure is that if I have a curve like this, right, that comes to a corner here, or a cusp, no matter what R you choose, it will not be smooth, right? You cannot possibly make a smooth parameterization out of a curve that is not smooth. Okay, so this will not be smooth. Right. But the green one, well, we don't know. It depends on what R is. It could be smooth, it might not be smooth. Okay? So yeah, it's not the curve that's smooth, it's the parameterization. Okay? And so here's a good example of that. I don't want to spend too much time on it, but this will illustrate the point. So we have two vector valued functions, right? And these will just be in a plane, not in space. The first one will be t squared, right? And then the second one, let's say u of t will be t cubed t to the sixth. Okay. So both of these vector value functions represent the same curve. In fact, we talked about this before, right? This is just the ordinary parabola, right? It's just y equals x squared. Both sides, symmetric, right? So, so that's the curve C represented by each of these parametrically. Let's say for all t, right? For all real numbers t here. Okay. So again, a parabola, usually you think of a parabola as a nice smooth curve. So are these vector valued functions, are they smooth? Well, let's look at the first one, right? What does it mean to be smooth? It means that the derivative is continuous. So we have to take the derivative. So what's the derivative of r? Well, it's 1, 2t, right? So 1 is the x component, 2t is the y component. Are these functions continuous? Well, yes, they are continuous. So part 1 is satisfied. The derivative is continuous. What about part 2? Part 2 says that this derivative can never be 0. Two times t, right. So does this equal 0, 0? No, never, right? Look, the y component could be 0. If t is 0, the y component is 0. But the x component is 1. And as far as I know, 1 is not equal to 0. So part 2 is satisfied, right? That this vector will never be equal to 0, 0. Right? It'll never be the 0 vector. Right? So yes, this is smooth. Right? It satisfies both parts 1 and 2. Right? What about the second example here? This u of t up over here. So I'm running out of space. Can I go down here? Right? So the first part, we have to take the derivative of, u. So u prime of t. So that's going to be 3t squared and then 6t to the 5. And of course, each component function, these are clearly continuous, right? I mean, they're not only continuous, they're differentiable. So we can take the second derivative and so on. Okay, so that's the first part. The second part is, does this equal 0? For any value of t, is this equal to 0, 0? Of course, absolutely. When t is 0, right? So u prime of 0 is equal to 0, 0. But that violates the second condition, right? The second condition is that the derivative can never be 0, but it is, right? So yeah, u, this vector valued function, is not smooth. In particular at 0, at t equals 0. It is smooth everywhere else, right? For every other t other than 0, the vector will not be 0, 0, right? But at t equals 0, this parameterization here, number 2, this is not smooth. Okay? Same curve, right? For the first curve, at 0, 0, at the vertex, right, at this point right here, at 0, 0, the first parameterization is smooth, but the second is not. So it's not the curve that we're talking about here. The curve may be smooth, it may not be smooth, but the parameterization is what's smooth. In the first example, the yellow case here, this is a smooth function. In example 2, it is not considered smooth because it violates that the derivative cannot be 0. Okay. Anyways, again, that's a distinction that for the most part is not going to come up again. So we don't have to worry about that most of the time. So I guess we'll look at some more examples. Okay, so this is a more familiar example, right? R of t is x is sine, y is cosine. And if that looks backwards to you, right, because usually x is cosine, y is sine, you'll see you get the same circle here, right? The radius is 1, so it's the unit circle. So let's say this is 1, 1, negative 1, negative 1. So notice what happens when t is 0, you're at x equals 0, y equals 1. So you're not starting over here, you're starting at the top, right here, the North Pole, right? And notice when t is pi over 2, sine of pi over 2 is 1. So x is 1, and y is 0. Cosine of pi over 2 is 0, right? So now you're over here. So you can see what's happening. You get the same circle, oops, but you're going clockwise instead of counterclockwise. And you're starting at the top instead of at the right-hand endpoint, right? So it's kind of a messy circle, but it is a circle, right? So yeah, it's the same circle, but a different parameterization, right? This is t equals 0. When you're over here, this is for pi over 2, pi over 2. When you get to pi, you're at the south pole. And when you get to 3 pi over 2, you're at the westmost point. And then obviously 2 pi, you're back up to the North Pole again. So yeah, you're going clockwise instead of counterclockwise, right? Okay, but what do we want to do? We want to take the derivative. And so the derivative of r, or r prime, if you like. I think you can handle that, right? Cosine of t, negative sine of t. And then for the second derivative, or r double prime of t, well, derivative of cosine is negative sine, derivative of negative sine is negative cosine of t. Right. And you'll notice something. You'll notice that the second derivative is actually just the original function, but with a minus sign. So it's negative r of t. Right. We'll come back to that later. What else do we want to do? We want to take the dot product of these two vectors, and I think we can do that. In fact, I'm going to do that way down here. Because this should be pretty easy, right? It's just going to be cosine times negative sine. So negative cosine times sine. And then plus a negative times a negative is positive. Sine times cosine, or cosine times sine, same thing. And you just get negative 1 plus 1 is 0. So the dot product here is 0. Right. And remember what that means. It means that the derivative, the first derivative and the second derivative are orthogonal, right? Perpendicular, right? So if this, at any given time, if this is r prime, then r double prime has to be perpendicular to r prime. Sorry, it's a double prime, right? Yep. So when the dot product is 0, the two vectors are orthogonal. That means the two arrows are at right angles. Okay. What about the cross product? Because we haven't done that in a while. So let's do the cross product of r prime and r double prime. I know these are both functions of t, but I don't want to squeeze that in there. So, oh, we can't do the cross product. Never mind. Okay. All right, bad question. There is no cross product here. It's impossible. Because, right, these are vectors in the plane, right? So this might be, well, we'll see this later. This might be r, right? And then this might be, oh, it's the other way, actually. This would be r prime. But these are vectors in the xy plane. There's no z components to them. So no, we cannot take the cross product. Sorry about that. right? Remember, the cross product is only defined, right, for vectors in space, right? Because they have to have an I component, a j component, and a k component. Okay, and these don't. So we're done with that. That's unfortunate. But you can still take the dot product, right, whether they're vectors in space or in the plane. Okay. So next we want to discuss some of the properties of the derivative of a vector-valued function. So we have two vector-valued functions, u and r and u, and let's suppose they're differentiable. So they're vector-valued functions of t, and w is a real valued function of t, right? So keep in mind we have r, which is a vector-valued function of t. We have u, which is also a vector-valued function of t. And then we have w, which is just an ordinary function of t. I would have preferred to use something like f to remind you that it's just an ordinary function. But okay, as long as you're comfortable that w is not a vector here, right? It's a scalar function. Right. So we have these three, we have two vector-valued functions and a real valued function. So the first property just says that if I take, and these are, these should be familiar to you. If I take the derivative of a constant, say c, times a vector-valued function, it's just the constant times the derivative of the vector, right? Constant times function rule, right? So same thing applies to vector functions, right? And then the sum rule also applies. So if I have two vector-valued functions, say r of t, and I add u of t to that, so if I want the derivative of that, I just add the two derivatives, right? So that's just the ordinary sum rule as it is in Calc 1, right? And of course you can also subtract too, so this is plus or minus, as the book also notes. Right? 3 is a little bit trickier because it's the derivative of a product, right? The product, you're multiplying a scalar function, w of t, times a vector function, r of t. Right? It's not a dot product, it's not a, right? Because it's a scalar times a vector. Right? Ordinary scalar multiplication. But it's still a product, so we have to apply the product rule, right? First times the derivative of the second, right? Plus second times the derivative of the first. Right. So that's rule 3 here, right? Rule 4 is now we're going back to the two vector-valued functions, and we're going to take the derivative of the dot product of the two functions. U of t, right? Right. It's still a product, so you still use the product rule, right? First times the derivative of the second. So by times, we mean dot product, the derivative of u, plus, right, the second dot the derivative of the first. So the derivative of the first is r prime, dot product with u. Right. Okay. So that's the product rule, applied to the dot product in particular. Okay. And it also works for the cross product, although we have to be a little bit more careful here. So the derivative of r cross u is going to be r cross the derivative of u plus the derivative of r cross u. Okay? And here you have to be careful, right? Because you can change the order of the sum. Right? You can change this with this. And you could have done that here too, of course, for the dot product, right? So you can change those, but what you cannot change is the order of the products, right? You cannot say this is u prime cross r, right? Or u, and then for the second one, u cross r prime. because remember, the cross product is not commutative. If you change the order, you're going to get a minus sign there when you don't want it. So yeah, here the order has to be maintained. For the dot product, though, the dot product is commutative. So you could change the order of these and these if you want. But to be consistent, we're going to keep the same order just as because we need that order for the derivative of the cross product, right? Okay, number 6 is the chain rule. So here we're taking the derivative of a function, a vector function, of a scalar function. So the chain rule says you take the derivative of the vector function and apply it to the scalar function, and then multiply by the derivative of the scalar function. Oh, yes, I'm sorry, no vector. It's not a vector w, right? It's just a scalar w. There we go. Phew. That was close. Yeah, no vector w, right? So this is not a dot product. This is not a cross product. And in fact, you can change the order, right? You can put the w prime first, although that's not how I usually remember the chain rule, but thinking of this as scalar multiplication, maybe it helps to do that. Okay, and number 7, the last one, and this is kind of an important one. If the dot product of R with itself, right, is equal to C, right? C is a constant, right? Then the dot product of R and its derivative has to be 0. The scalar 0, right? Not a vector 0. Okay, so 7, I think, bears a little bit of explaining, because I think the other ones, these just come from ordinary calculus, right? You're just applying them over 3 components instead of just 1 component from Calc 1. Okay, but 7 is a little different, right? 7 is weird. So just as an example, right? If you have a vector valued function, let's make it simple. How about t squared, right? The parabola. Right, so just 2 components here. If I take the dot product of that with itself, what do I get, right? I get t times t, which is t squared, plus t squared times t squared, which is t to the 4th, right? And this is not a constant. Right? This is not a c here, right? In general, what you're going to get when you take the dot product of R with itself, you're going to get a scalar function, right, like t squared plus t to the 4th. Okay, so it will depend on t. Different t's give you different values. Okay. On the other hand, for other functions, and maybe let's go to another example. How about the one we just did, sine and cosine? Right. So if we take the dot product of this R with itself, what do we get? We get sine times sine, so that's sine squared of t, plus cosine times cosine, which is cosine squared of t. So this is a function of t, but it's a constant function. It's equal to 1. Right? So here, the dot product of R with itself is a constant. It is a number. It does not depend on t. So the conclusion is, if we took the dot product of R with its derivative, we would have to get 0. And in fact, I think we did that. Well, no, we didn't do this one, but so let's do it, right? What is the derivative of R? Right, it's just cosine times negative sine. Sorry, not times. The x component is cosine, the y component is sine. Right, you're not multiplying. So the dot product of R with its derivative is just going to be sine times cosine plus negative sine times cosine, which of course is 0, as promised. Right, that dot product would have to be 0. Okay, anyways, that doesn't prove it, but that just shows that it's true for this particular example. So let's prove it. We're not going to prove the others, but I think number 7, we should prove that one. Right? And in fact, it's not a hard one to prove, right? You'll notice that on the left side, we have, right, so if we're supposing that the dot product of R with itself is equal to a number, we'll call it C, some constant C. So how do you get R times the derivative? Well, if you noticed, back in number 4 here, if you take the derivative of the dot product of two vectors, you get a vector times its dot product, times its derivative, right? Sorry. You get a vector dot product with its derivative. Okay, so I think what we want to do here is just take the derivative of both sides, right, with respect to t here. Right. So on the left side, we're just going to apply rule 4 here, which says that we take r dot r prime, so this is equal to r of t dot r prime of t, plus r prime of t dot r of t. On the right side, you get, well, the derivative of a constant is 0. Okay. So let's look at the left side. Remember, the dot product is commutative, right? So I can switch the order if I want. And I do want to do that. I want to change the order here. I want to make this r dot r prime, right? And that's still equal to 0, right? So we talked about that way back in chapter 11. U dot v is v dot u, so you're allowed to do that here, right? And notice that these are the same thing, so you're just adding 1 plus 1. So we have 2 times r oops, I forgot the dot product here. Dot product with r prime. And that's equal to 0. So just divide both sides by 2, and that tells us that r dot r prime of t has to equal 0 as a scalar, as a number. Okay, so that proves it for any r. And we looked at this particular r where it's true. Of course, this example here, the condition is false, right? That this t squared plus t to the 4th is not a constant. So if we were to take the dot product of r and r prime, we should not expect to get 0. In fact, we probably don't. Maybe at a specific value of t, but not for all t, right? This is true for any t, right? This is true for all t, at least all t in the domain, whatever the domain is. Okay, so yeah, so this I think is a good illustration of these properties here. Do you have to know them? Well, they're not on your formula sheet, so yeah, you probably should know these. I mean, look, should you know the product rule for Calc 1? Of course. Should you know the quotient rule? Should you, right? So why don't we have a quotient rule here? I guess that's a good question. But anyways, you should know these, but, for the most part, they're kind of intuitive, right? In other words, you can't go wrong when you apply, say, the product rule to the dot product or the cross product or the chain rule. It works exactly as you would expect. So if you know the product rule from Calc 1, you know these rules, right? If you know the sum rule for Calc 1, you know these rules, right? The only different one, I think, is number 7. And we spent a lot of time on that, so hopefully that will become a little more clear as we go on. Okay, so I think we've talked about derivatives enough. What about antiderivatives? What about integrals, right? So you have a vector valued function, and as long as r is continuous, it's integrable. right? So we're not going to get into integrability. Basically, all continuous functions are integrable, right? Whether or not they're differentiable doesn't matter. And so you can talk about the indefinite integral, right? So this is an indefinite integral. Right? And it applies just as it would be for derivatives, right? You just add the component functions as you take the integral of each component function separately, right? And you can do the same for definite integrals. Remember, a definite integral, these will just end up being numbers. So this will be some vector, right? 3i plus 4j minus 6k, for example, right? So, yeah. So it works for indefinite integrals, definite integrals, right? So might as well start with a good example here. Suppose we want to, well, okay, so suppose r is the vector valued function. Let's do e to the 2t times I plus t to the 4 times j plus something unusual. How about hyperbolic sine of t times k? And I think not that long ago I said we're not going to worry about hyperbolic sine and cosine very much, but you know, if it comes up, look, you can always look it up, right? It shouldn't be hard. So what do we want to do? Let's find the indefinite integral of r. Okay, and then we can do a definite integral later. Yeah. So this will just be another vector valued function. Let's call it u of t. It will be the indefinite integral. And of course, we just take the indefinite integral of each component function. So for the x component, I think we get 1/2 e to the 2t, right? Plus c, don't forget, right? Because these are indefinite integrals, so don't forget your plus c here, times I. And then the integral of t to the 4th, so that's going to be 1/5 t to the 5th, plus c. Now, might not be the same c, so how about c1 and then c2 here? So it'll be plus j, times j. And then, well, the derivative of sinh is cosh, and the derivative of cosh is sinh. So this will be a plus hyperbolic cosine of t plus c3, right, times k. Okay. Now, the c1i plus c2j plus c3k, this is a constant, but it's a constant vector. Okay. So we can basically treat all the c's as a single constant vector. So what we could do is write it this way: 1/2 e to the 2t times I plus, let's say, 1/5 t to the 5th times j plus hyperbolic cosine of t times k, and then plus the vector c, right? So by the vector c, I mean the vector with components c1, c2, and c3. Okay, so you can always do that. You don't have to put the c's under the individual components unless you want to, but not necessary, right? Okay, how about a definite integral? I think I have enough space for that. So yeah, we should use a different r here. Something nicer. How about 2t, 3t squared, and how about 8t cubed? Okay. So suppose we want to find the definite integral. Let's just do 1 to 2 of r of t. Okay. So yeah, this will not be a vector. Well, it will be a vector, I'm sorry. It will be a vector, but not a function, right? It'll be a vector as components will just be numbers, right? So let's work this out, right? This is just going to be from 1 to 2, right? So what are well, let's do the fundamental theorem of calculus, right? The indefinite integral will just be t squared, t cubed, and then 2t to the 4th. And by the fundamental theorem of calculus, we just plug in the 1 and the 2 and then subtract, right? So let's see, when you plug in 2, you get 4, 8, and 32. When you plug in 1, you get 1, 1, and 2. So when you subtract, you get 3, 7, 31. Right. So it is a vector, but it's a constant vector. It doesn't depend on t, of course. Right? And there's no c here, right? It's a definite integral. But whether you write it this way or this way is completely up to you. As I said many times, I will go back and forth between the two, and so either way you write it is okay with me. But yeah, don't try to mix them up though, right? Every once in a while I get students getting them confused, and they write this. Right, you don't. If you're doing this, you don't need brackets, right? And you know, if you're doing, obviously, if you're doing this, then you need the I, J, and K, because 41 is not a vector, right? So yeah, without the I, J, and K, that's also wrong. So yeah, don't get confused between the two notations. If you want to stick with just one and ignore the other, that's fine. However, I am going to go back and forth constantly. Right. So I hope that helps for indefinite integrals and definite integrals. And oh, we did a lot here, so I think we'll do one more. Okay, so I don't think I do enough of these, right? True or false? The derivative of the magnitude of r is equal to the magnitude, or the norm, of the derivative of r, right? So another way to write the norm of the derivative, we could just write the magnitude of r prime, if you will, right? But does that equal the derivative of the norm of r itself, right? So true or false, what I mean is, is this always true for any vector valued function? Okay, so why don't we just start by making up an example here? All right, let's keep it as simple as possible. How about just 2t and then t plus 1? Right. So let's calculate both of these, right? First of all, what's the magnitude of r? Right, so it's just the square root of 2t squared plus t plus 1 squared. And we might as well multiply that out here just to simplify a little bit. So what do we get? I think we get the square root of 4t squared plus t squared is 5t squared plus 2t plus 1. Okay, now let's do the right-hand side, right? I'm sorry, we're not done with the left side. We have to take the derivative of that. Oops, we have to take the derivative of the magnitude of r. Okay, so this is a Calc 1 problem. So this is where it probably helps to think of this with an exponent of 1/2 and just use the power rule, right? And then the chain rule, so 10t plus 2. So I think if we simplify, we get 5t plus 1 all over the square root of 5t squared plus 2t plus 1. Okay, so that's the left side, right? So this is the left-hand side, right, of this equation up here. Now we have to do the right-hand side. So first we need r prime. So let's use a different color here. So r prime is just 2 and 1. Okay, now take the magnitude of that. The magnitude of the derivative, it's just the square root of 2 squared plus 1 squared, right? It's the square root of 5. Well, clearly that's not equal to, right, so this is the right-hand side, and that's not equal to the left-hand side. So whatever you say, this does not equal this. Okay, well, in general, right? Oh, there could be maybe one value of t where this is true. You could try to solve that equation for t, and you might come up with a value. And it may be, there may be two of them, right? Because it could be quadratic. I don't know. But this is certainly not true for all t, right? And that's kind of the point here, right? So look, it's false for this example, right? It might be true for other examples, maybe simpler ones, but it's not true in general. So this is false, right? This is definitely false. For any r of t, we picked a good one where it turns out that they were not equal, right? Because if we picked one where they are equal, where this is true, well, that doesn't prove that it is true. It just means it's true for that one example. Then we have to find another example and another example. And, if you find 100 examples where this equation works, that you still can't say it's true, right? So in that case, you might actually have to prove that it's true. And that's a harder thing to do here. The way to go about it, of course, I think, is write them in terms of their components. And if you write these in terms of their components, you'll see what goes wrong with what's different about the left side and the right side. Right? And in fact, that would give you a good indication of when it might be true. For what particular examples for R would these be equal? And because it's not true in general. It's certainly not true for this example here. So that would be a challenge problem, right? For what t, right, for what r of t is the magnitude of the derivative. Well, I think I got it backwards, right? I want the derivative of the magnitude of r. When does that equal the magnitude of the derivative of r? So there are some vector valued functions for which this is true, but they're very special cases. And if you can determine what that special case is, then you're very good, because this is a challenge. So you don't have to do it, but it's if you can manage to do it, then great. Okay, so again, even this problem, the true or false, is something you have to think about. It's not a trivial problem either. But that should be it for this section. And in the next section, we'll figure out what these vector valued functions are all about. And I've already sort of alluded to it, that they describe a point or a particle moving in space. Right, so it's going to describe motion. So stuff moving. And when something's moving, you might want to know how fast it's going, its velocity or acceleration. Okay, so that'll be the next video, the next section.